Ladies and gentlemen, today we're going to talk about lenses, and we finished our discussion of mirrors. The big driver for lenses is, of course, Snell's law, so n1 sine theta 1 equals n2 sine theta 2. But we're not going to actually do the calculations. We just want to see how the light passes through, just in a general manner, and then that'll help us figure out some applications for lenses. So instead of using the complete law, we'll just think about what it tells us. And what we know from our refraction studies is that if we go from a high-speed medium to a low-speed medium, the angle gets smaller. So if this is the ray of light heading in this way, when we draw a normal line in, it's going to go to a smaller angle, like that. And then, of course, the reverse would be true. If we go from a low-speed medium into a higher-speed medium, we're going to bend to a larger angle, so like that. So with that idea, which does come from Snell's law, we're going to be able to figure out lenses. Now with the lens, we've got two different types of lenses. In mirrors, we had three types because we had a plane mirror. Unfortunately, well, I don't know if it's unfortunately but a plane lens doesn't really do anything at all, right? A light ray traveling into a device like this just comes out at the same angle it came in at. So that's not super interesting. There's a little refraction there, but same angle. So instead, what we're going to look at is we're going to look at converging and diverging lenses. So converging lens and a diverging lens. Now the converging mirror was called a convex mirror, and a diverging lens was called a converging mirror was a concave mirror, and a diverging mirror was convex mirror. It's the opposite for the names here. So converging was convex, and now converging is concave. Oops, convex. Sorry. And this would be our concave. Okay, so again, it just has to do with the shape. So our convex lens is going to look like that, and our concave lens is going to look like that. So remember, the convex mirror had that curved shape outside, just like that, and the concave mirror had that curved shape inside. Obviously, we're going to draw a little bit better pictures, but what we're going to do is we're going to draw our parallel ray diagrams and our image diagrams for these two objects, and that'll hopefully give us a good idea about what they're used for. And then we'll talk a little bit more about the human eye when we get there. So let's start off with that convex lens. And so for our convex lens, is that shape there. Now convex lenses don't have to have the same radius for each curve. In fact, it's really common for them to not, but we're just going to make them be the same in this case. Again, just like we've done before, we're going to draw an axis of symmetry down the center to help us a little bit. And we always want to start with our parallel ray diagram. So I'm going to send in 3 parallel light rays. Now you can send them in any different direction, but for me, it's going to be a lot easier if we do one along our axis of symmetry, because there'll be very little I have to draw for that one. This is our parallel ray diagram. Okay, so remember, we're talking about refraction now, because this light, it's not a mirrored surface. The light can actually pass into this new material. So we've got air or vacuum out here, we've got some sort of glass here, and then air and a vacuum out here. So that means our wave is slowing down, which means it's going to bend towards the normal, smaller angle. Well, when we look at this one, this is actually at 0 degrees already. Right? It's right on that normal line. So if it's on the normal line, and it's at 0 degrees, you can't go any more than 0 degrees, so it's going to refract also at 0 degrees. It stays right on the axis of symmetry. And then again, same thing on the way out. It stays on the axis of symmetry. So if we plug into Snell's law, n1 sine theta 0, we end up with a sine of 0 out on the way out. Same thing the whole way through. So that ray of light goes straight through. Now these other rays of light, we're going to have to draw our normal lines. So a normal line, again, is a line drawn perpendicular to the surface, which in the case of a curved surface like this, you have to imagine a tangent line like that, and then draw a line perpendicular to a tangent line. So I think I did a pretty good job. And so now we're going to go from an angle, I don't know, that looks like maybe 30-ish degrees. So it has to go to a smaller angle. So a smaller angle maybe looks like that. And so again, if we imagined, I don't usually like to put these on my diagram, but let me just show you. See how the angle definitely got smaller. Same thing here, very similar, like that. And so you can see why these convex lenses are called converging lenses. Those parallel rays are starting to come together. Now let's see what happens when it travels back out. So again, I've got to draw a new normal line perpendicular to the surface, and it has to go to a bigger angle. So this line right along there would be no change. So if this is going from glass into the same glass, no change. But it's got to go to air, which has a higher velocity, so therefore a higher angle. So a higher angle would be something like this. So I'm going to cut that in this direction, like that. If I do the same thing here, and again, if we used a ruler and a protractor, you could prove to yourself that it actually works out. But if we do, what we get is we get convergence of the light. And if you remember from our mirror discussions, when the spot where parallel light rays actually converge, we call that point the focal point. So that's our focal point right there. So same kind of uses. When we think about an application of this, we're taking all of this light, which would have been spread over a large surface, and concentrating on a single infinitesimally small point. And so what light does, light carries energy. We know that light, if we put our hand out in the sunlight for a little while, it's going to heat us up. If we were to put our hand exactly at that spot, it would burn our hand. And I'm sure you guys are all nice kids, so you've probably never done it before, but if you had a magnifying glass, which has a convex lens like this, and you took it out in the sun, and you had, say, like a little ant or something on the ground, if you move that lens back and forth until you see the ant get really bright, you could, if you wanted to, catch the ant on fire. Now, I can honestly say I've never done that, but I have done that demonstration before with little pieces of paper. So if you take some small piece of paper, especially dark colored piece of paper, because white reflects light. But if I take, say, a piece of paper and I color a little spot of it dark like that, and I place it at the focal point, that would result in almost an immediate fire. Sorry. So, a convex lens takes parallel light rays and converges them. Okay, so parallel light rays are converged to the focal point by the convex lens. Sorry, I got that below the screen. Okay, so let's see what happens if we put an object somewhere out here. So again, with our next diagram, we're going to draw this nice lens, and we're going to put an object there and see what happens. So let's see. Let me try to draw my lens again. I was happy with my last one. That was not terrible. And we'll draw our axis symmetry here. Ooh, it's a bad axis symmetry. And we'll put our object somewhere in here. So just for reference purposes, because light can travel through in either different direction, right? I could have light shining this way or light shining this way. That means it'd be a focal point on each side. And if the two radiuses were the same, we'd have the same focal point. Okay. So what I'm going to do is I'm going to place an object somewhere outside of the focal length here. Here's my object. And what I'll do is I'll send, just like I did with my mirrors, 3 different light rays. Almost every time I send a second one, but we'll see. Just like that. Now we know what's going to happen for the one along the axis of symmetry. It should pass straight through, just like that. This one now, again, we'd like to send that ray down because it's already got its own We don't have to draw a new normal line because we can use the axis symmetry as a normal line. So that angle is small, but it's got to go to an even smaller angle because it's slowing down. And that looks like I did that pretty well, right? Maybe that's 40-ish degrees, and that's like 15 degrees. Then I've got to draw a new normal line here. So let's see, pretty small angle. But it's got to go to a bigger angle. So let's say something kind of like that. Now this one I do have to draw a normal line for. And the nice thing about this, and again, there's a reason why physicists are pretty smart people here. And so this line, we already know where it's going to go. I mean, I'm going to draw it all the way through, but this one was parallel to this. And so we remember that parallel light rays will end up through our focal point. So eventually it's going to pass through that point there. So that means that if I do this process, and I do a pretty good job of it, it should pass through the focal point. Now, I had to extend my picture a little bit, but hopefully what you see is these two light rays do intersect. And we know where two light rays intersect. That means that, and again, we could draw a third one if we want and trace it through. It would also intersect there. Anything from that point will intersect at that position. Excuse me. So that tells us if there's an actual intersection, that means people looking into this device, it would seem to them like we've got an image or an object here at that position. So this is our image. And our image is upside down, and it's an actual convergence. So what we end up with is, you could say, objects placed outside the focal point result in real inverted images. Now, one of the things that I want you to notice about this, because this is going to become super important for us soon, is that these two light rays from this object where it's located converge at a very specific point. If I were to, and it would take us a while, but if I move that object, say I move the object a little bit closer like this and went through that whole same process, what I'd find is that it wouldn't focus right there. It would focus somewhere else, most likely a little bit further outside here. So depending on where our object is in relation to our mirror, our image is going to appear at a different spot. And so what that means is that for a lens like this, the image appears at a very specific position. And so if we're not trying to read that image at that exact position, it's going to be blurry. It's not going to actually converge. Now, what's blurry mean? Well, if I were to put my eyes right about here where my pen is, these two light rays, the light ray on top and the light ray on the bottom, would both fall in two different spots in my eye, which means when I looked at it, I'd have kind of a double vision effect. It would seem to me like the tip of this object that I was looking at was in two different locations. And in fact, if we sent more and more light rays, it would seem like that tip was in a lot of different locations. So we couldn't resolve that. Our brain would see that as a really blurry position. But if we moved our eye back to this position, where all those light rays converge, it would seem to be a nice clear image. So in here, it would be blurry. Right there, it would be exactly on, and then obviously if we went in the other direction, it would be blurry. What I'm going to do is I'm going to press the autofocus button. I'm going to press the autofocus button here on my overhead camera, and what you see is as it moves back and forth from one position to another, what it's doing is it's physically moving, it's physically moving the camera, the lens inside the camera. It's actually the little reader, but it's moving that up and down. And so when it moves it to different positions as it tries to focus, it's making it blurry or sharp, And once it finds that spot where those light rays are converging, we get a nice clean image. And that's what our human eye does as well. So when we look at objects are really typically that we're looking at are pretty far away from our eye. So this is our eyeball here. Let me turn it into an eyeball. This is our eyeball. We're usually going to look at things that are pretty far outside our focal length. So what that means is if those objects are falling exactly on our sensors back here, so we've got our rods and cones back in that position. If our object is falling, in this case, not exactly on those rods and cones, it would be blurry. And we can make some change to our lens, which we'll talk a little bit more about, to get that to fall exactly in that position. So that's what happens if the object is placed outside the focal length. Now let's see what happens if we place our object inside the focal length. So what I'm going to do for that is I'm going to kind of flatten my lens out a little bit here just to make it easier to try to put it inside the focal length. And draw my axis of symmetry. Let's say that the focal length is out here now. I'm going to draw my object inside that focal length. So maybe I'll right in here like this. And I'll send my light ray there, there, and on the bottom. Okay, so this one has to go through the focal point. Now, what I'm going to do is I'm just going to cheat it a little bit because I made my focal point pretty far away, like that. So that's a questionable refraction there, but it got to my focal point. And what I'll do is I'll look at what this light ray does. So this light ray is coming in at a pretty big angle, with respect to the normal line. It's going to bend to a smaller angle, like that. And then on the way out, it's going to bend to a bigger angle again. And so hopefully what you see is that these two light rays that start from the tip diverge. Right, this light ray is headed off here. This light ray is headed off down here. So they're diverging. There's no actual convergence of the light. So what do we do about that? Well, we've seen that with the plane mirror, and we've seen that with the convex mirror before. And so we should have a decent idea about what that means when we look at this idea. So what we'll do is we'll imagine looking into our lens. So we're looking into our lens along this line. So that means a ray of light which originated at the tip. We see the tip. If we look along this line, our brain tells us the tip falls somewhere along that line. Our brain here tells us, looking in this line, that the tip of this arrow, our object, falls somewhere along this line. And so if we trace these lines back, just like this, our brain says this appears somewhere along this line, this appears somewhere along this line. And hopefully what you see is we see a virtual convergence of the light. So again, if we use rulers and protractors and we drew these lines nice and straight, that one's not very straight, but we see that we have a virtual image here. And what do you notice about that image? Well, it sort of looks like it's on the exact same position. Now that's just dumb luck based on my diagram. It won't always be in the exact same position, but hopefully what you do notice is that it's significantly larger. So an object placed inside the focal length results in an image that is right side up, virtual, and larger. And that seems like a pretty easy application for us, right? This is literally a magnifying glass. So if you imagine using a magnifying glass, which you've used in science before, and you place the object that you're interested in pretty close to the magnifying glass, and you look in this direction, you get a larger image, magnified image, and a right side up image. And so when we think about these convex lenses, what a convex lens does for us is our convex lens will, when placed outside the focal length, flips our image over but makes it real, so it can be projected on something, like on the back of our eye. And when it's placed inside that, we get an enlarged image. What I think I'm going to do is I'm going to stop this video now, and we'll make another video looking at the other type of lens. Have a great day, everybody.